Welcome to our deep dive into computer architecture. In this video, we'll explore the fundamental building blocks that make up every computer system. From the smallest embedded devices to the most powerful supercomputers, computer architecture defines how hardware and software interact to process information. Understanding these concepts is crucial for anyone interested in technology, programming, or engineering. We'll start by defining what computer architecture is and why it matters in the digital age. Then, we'll break down the main components, discuss their roles, and see how they work together to execute instructions. Let's begin our journey into the fascinating world of computer architecture. Computer architecture refers to the design and organization of a computer's core components. It's like the blueprint for how a computer works, specifying how the processor, memory, and input-output systems communicate. This field covers both the hardware, the physical parts you can touch, and the low-level software that controls them. By understanding computer architecture, we can appreciate how computers perform complex tasks quickly and efficiently. This knowledge also helps engineers design better, faster, and more reliable systems. Next, let's look at the main elements that make up a typical computer architecture. The heart of every computer is the central processing unit, or CPU. Often called the brain of the computer, the CPU carries out instructions from programs by performing basic arithmetic, logic, control, and input-output operations. It's made up of several key parts, including the arithmetic logic unit, ALU, control unit, and registers. The CPU's speed and efficiency play a huge role in overall system performance. As we move forward, we'll see how the CPU interacts with other components to process data and run applications. Memory is another essential part of computer architecture. Computers use a hierarchy of memory types, each with different speeds and sizes. At the top, we have fast but small caches, followed by main memory RAM, and finally larger but slower storage like hard drives or SSDs. This hierarchy ensures that the CPU can access data quickly when needed, while still having plenty of space for programs and files. Understanding how memory is organized helps us see why some computers feel faster than others, and how data moves through a system. Random access memory, or RAM, is the main memory used by computers to store data temporarily while programs are running. RAM is much faster than storage devices, allowing the CPU to quickly read and write information it needs right now. However, RAM is volatile, meaning all data is lost when the computer is turned off. The amount and speed of RAM can greatly affect how many programs you can run at once and how smoothly your system operates. Next, we'll look at how storage devices complement RAM. Storage devices, such as hard drives and solid-state drives (SSDs), provide long-term data storage for your computer. Unlike RAM, storage keeps your files, programs, and operating systems safe even when the power is off. SSDs are much faster than traditional hard drives, which can make a big difference in how quickly your computer boots up or loads applications. The balance between RAM and storage is a key part of computer architecture, ensuring both speed and capacity for users. Input and output (I/O) devices connect the computer to the outside world. Input devices like keyboards and mice let users interact with the system, while output devices such as monitors and printers display results. The architecture must efficiently manage data flow between the CPU memory and these devices. Modern computers use various buses and controllers to handle I/O operations, ensuring smooth communication and responsiveness. Next, we'll see how these components are connected inside the computer. Motherboard is the main circuit board that holds and connects all the computer's components. It contains slots for the CPU, RAM, storage, and expansion cards. Buses are electrical pathways that transfer data between these parts. The speed and design of the motherboard and its buses can significantly impact system performance. By organizing components efficiently, the motherboard ensures that data moves quickly and reliably throughout the computer. Let's now explore the different types of buses used in computer architecture. There are several types of buses in a computer system, each serving a specific purpose. The data bus carries information between the CPU, memory, and peripherals. The address bus specifies where data should go, while the control bus manages commands and timing. Modern computers may also use high-speed buses like PCI Express for graphics cards and other expansion devices. Understanding these buses helps explain how data travels efficiently within a computer. Instruction Set Architecture, or ISA, defines the set of commands a CPU can execute. It acts as the interface between hardware and software, allowing programmers to write code that the processor understands. Different CPUs may use different ISAs, such as x86 or ARM, which affects compatibility and performance. The ISA determines how instructions are formatted, how data is accessed, and how operations are performed. Next, we'll look at how instructions are processed inside the CPU. CPU operates using a cycle known as fetch, decode, execute. First, it fetches an instruction from memory. Next, it decodes what the instruction means. Finally, it executes the instruction, performing the required operation. This cycle repeats millions or even billions of times per second, allowing computers to run complex programs. Understanding this process is key to grasping how software is translated into actions by the hardware. To improve performance, modern CPUs use a technique called pipelining. This means that multiple instructions are processed at different stages simultaneously, much like an assembly line. While one instruction is being executed, another can be decoded and a third can be fetched. Pipelining increases the number of instructions completed per second, making computers faster and more efficient. However, it also introduces new challenges, such as handling instruction dependencies and hazard. Superscalar Architecture takes pipelining a step further by allowing multiple instructions to be executed in parallel during each clock cycle. This is achieved by having multiple execution units within the CPU. Superscalar processors can issue and complete more than one instruction at a time, significantly boosting performance. However, designing these systems is complex, as the CPU must manage dependencies and resource conflicts efficiently. Modern CPUs often contain multiple processing cores on a single chip. Each core can execute instructions independently, allowing for true parallel processing. This is especially useful for multitasking and running complex applications that can take advantage of multiple threads. Multicore processors have become standard in everything from smartphones to servers, enabling faster and more efficient computing. Cache memory is a small, high-speed type of memory located close to the CPU. It stores frequently used data and instructions, reducing the time needed to access information from main memory. Caches are organized in levels L1, L2, and sometimes L3, each with different sizes and speeds. Efficient cache design is crucial for maximizing CPU performance and minimizing delays. Virtual memory allows computers to use storage devices as an extension of RAM. When physical memory is full, the system moves data to a special file on the hard drive or SSD, called a swap file or page file. This lets users run more programs than would otherwise fit in RAM, though accessing virtual memory is much slower. Virtual memory management is a key part of modern operating systems and computer architecture. Input-output controllers are specialized chips or circuits that manage communication between the CPU and peripheral devices. They handle tasks like reading from a keyboard, writing to a disk, or sending data to a printer. By offloading these tasks from the CPU, I/O controllers help improve overall system efficiency and responsiveness. Let's now look at how computer architecture has evolved over time. Computer architecture has come a long way since the early days of computing. Early computers used vacuum tubes and relays, which were large and slow. The invention of the transistor and integrated circuits revolutionized the field, making computers smaller, faster, and more reliable. Today, advances in semiconductor technology continue to push the boundaries of what's possible, enabling powerful devices that fit in our pockets. Von Neumann architecture is a classic computer design model that forms the basis of most modern computers. It features a single memory space for both instructions and data, with a CPU that fetches and executes instructions sequentially. While simple and flexible, this design can suffer from bottlenecks when the CPU waits for data from memory. Many modern systems use variations of this architecture to improve performance. Harvard architecture is another important computer design, featuring separate memory spaces for instructions and data. This allows the CPU to fetch instructions and data simultaneously, improving speed and efficiency. Harvard architecture is commonly used in embedded systems and microcontrollers, where performance and simplicity are critical. Let's compare these two architectures in more detail. Comparing von Neumann and Harvard architectures highlights their strengths and weaknesses. Von Neumann's unified memory is flexible but can create bottlenecks, while Harvard's separate memories offer faster performance at the cost of complexity. The choice between these designs depends on the application's needs, with many modern systems blending features from both to achieve optimal results. CISC reduced instruction set computer and CISC complex instruction set computer are two major CPU design philosophies. RISC uses a small set of simple instructions, making CPUs easier to design and faster for certain tasks. CISC includes more complex instructions, allowing for more powerful operations in a single command. Each approach has its advantages, and modern CPUs often combine elements of both. Microarchitecture refers to the specific implementation of a processor's architecture. While the architecture defines what the CPU can do, the microarchitecture determines how it's built. This includes details like pipeline depth, cache size, and execution units. Different microarchitectures can implement the same instruction set in various ways, affecting performance, power consumption, and cost. System on chip, or SoC, integrates all major components of a computer onto a single chip. This includes the CPU, memory, storage controllers, and often graphics and networking units. SoCs are widely used in smartphones, tablets, and other compact devices, offering high performance and low power consumption in a small package. Graphics Processing Unit, or GPU, is a specialized processor designed for handling graphics and parallel computations. Originally used for rendering images and video, GPUs are now essential for tasks like gaming, scientific computing, and artificial intelligence. Their architecture allows them to process thousands of operations simultaneously, making them much faster than CPUs for certain workloads. Embedded systems are computers built into other devices such as cars, appliances, and industrial machines. These systems are designed for specific tasks and often use simplified architectures to save space and power. Embedded systems are everywhere, quietly powering the technology we rely on every day. Parallel computing involves using multiple processors or computers to solve problems faster. By dividing tasks among several processing units, systems can handle larger workloads and complete jobs more quickly. Parallel computing is essential for scientific research, big data analysis, and high-performance computing applications. Cloud computing relies on distributed computer architecture to deliver services over the internet. Data and applications are stored on remote servers, which users access from anywhere. Cloud architecture uses virtualization, load balancing, and redundancy to provide scalable, reliable, and secure computing resources for businesses and individuals. Networking connects computers and devices, enabling them to share data and resources. Computer architecture must support network interfaces, protocols, and security measures to ensure fast and safe communication. From local area networks, LANs, to the global internet, networking is a vital part of modern computing. Security is a critical consideration in computer architecture. Systems must be designed to protect against unauthorized access, data breaches, and malware. This involves both hardware features like secure boot and encryption and software measures such as firewalls and antivirus programs. Secure architecture helps keep users' information safe and systems reliable. Power efficiency is increasingly important in computer architecture, especially for mobile and embedded devices. Designers use techniques like dynamic voltage scaling, sleep modes, and efficient circuit layouts to reduce energy consumption. Lower power usage extends battery life and reduces heat, making devices more practical and environmentally friendly. Moore's law is an observation that the number of transistors on a chip doubles roughly every 2 years, leading to exponential growth in computing power. This trend has driven rapid advances in computer architecture, enabling faster, smaller, and more affordable devices. However, physical limits are making it harder to maintain this pace, prompting new innovations in design and materials. Quantum computing represents a radical shift in computer architecture. Instead of traditional bits, quantum computers use qubits, which can represent multiple states at once. This allows them to solve certain problems much faster than classical computers. While still experimental, quantum computing has the potential to revolutionize fields like cryptography, optimization, and simulation. Artificial intelligence, AI, is driving new developments in computer architecture. Specialized hardware such as AI accelerators and neural processing units is designed to handle the massive computations required for machine learning and deep learning. These innovations enable faster training and inference, powering applications from voice assistants to autonomous vehicles. Reconfigurable computing uses hardware like field programmable gate arrays, FPGAs, that can be reprogrammed for different tasks. This flexibility allows systems to adapt to changing requirements, offering a balance between performance and versatility. Reconfigurable architectures are used in research, communications, and specialized computing applications. Fault tolerance is the ability of a computer system to continue operating even when some components fail. This is achieved through redundancy, error correction, and backup systems. Fault-tolerant architectures are essential for mission-critical applications such as banking, healthcare, and aerospace, where downtime is not an option. Scalability refers to a system's ability to handle increasing workloads by adding more resources. Scalable computer architectures can grow from small setups to massive data centers, supporting more users and applications as needed. This flexibility is vital for businesses and cloud providers who must adapt to changing demands. Performance metrics help evaluate how well a computer system operates. Common metrics include clock speed, instructions per second, memory bandwidth, and power consumption. By analyzing these factors, engineers can identify bottlenecks and optimize system design for better speed, efficiency, and reliability. Instruction-level parallelism, ILP, is a technique that allows multiple instructions to be executed at the same time within a single CPU core. By reordering instructions and using advanced scheduling, CPUs can make better use of their resources and boost performance. ILP is a key feature in modern processor design. Branch prediction is a feature in modern CPUs that guesses the outcome of conditional instructions to keep the pipeline full. Accurate branch prediction reduces delays and improves performance, especially in complex programs with many decision points. Advanced algorithms and hardware are used to make these predictions as accurate as possible. Out-of-order execution allows CPUs to process instructions as resources become available, rather than strictly following program order. This helps avoid delays caused by waiting for previous instructions to finish, making better use of the CPU's capabilities. Out-of-order execution is a hallmark of high-performance processors. Direct memory access, or DMA, is a feature that allows certain hardware components to access system memory directly, without involving the CPU. This speeds up data transfers for devices like disk drives and network cards, freeing the CPU to handle other tasks. DMA is an important part of efficient computer architecture. Bus arbitration is the process of managing access to shared communication pathways, or buses, in a computer system. When multiple devices need to use the bus at the same time, arbitration ensures that data is transferred efficiently and without conflict. Effective bus arbitration is crucial for maintaining system stability and performance. Future of computer architecture is full of exciting possibilities. Emerging trends include neuromorphic computing, which mimics the human brain, and 3D chip stacking for greater density and performance. As technology evolves, architects will continue to find new ways to make computers faster, smarter, and more energy efficient. We've covered a lot of ground in our exploration of computer architecture. From the basics of CPUs, memory, and storage, to advanced topics like parallel computing and AI hardware, architecture shapes the capabilities of every computer system. Understanding these concepts helps us appreciate the incredible technology that powers our world and prepares us for the innovations yet to come. Thanks for joining us on this journey through computer architecture.